All right, good morning. Let's begin. I've just handed out a copy of the lab experiment that we're going to run this week. It's a slight change from what was originally on the schedule. The schedule said that we were going to do Water Gems 1 this week, but I've switched it so we'll do the Hydrostatic Force Lab this week and then we'll do Water Gems next week. So along with that, be expecting an email from me that has some instructions on how to download and install Water Gems. It's one of the free software packages that you're entitled to because you pay tuition at Marshall. You get all these free software packages, and Bentley Water Gems is one of them. All right, so what we will be doing is the Hydrostatic Force Lab. Remember that I see some of you at 2 o'clock, some of you at 3:30 today, and then also tomorrow. I also handed out a rubric that's used for grading the full lab reports. Now, the lab submission that you're doing today isn't a full report. It's kind of an abbreviated assignment that has some specific questions along with it. But for the hydrostatic lab that you're going to be doing today, you'll need to write a full report that has, for example, an introduction section, a description of the methods, the results presented in tabular format, a write-up of the conclusions, and so on. And the expectation for what should be in your report can be described in this handout. This is a rubric that we developed as part of our ABET assessment. In this course, your ability to design and conduct lab experiments is described on this rubric. And so, for example, if you want to be outstanding, then you can see what are the characteristics for outstanding, satisfactory, marginal, unsatisfactory, and so on. Okay, one important thing I'm going to point out is that some of these descriptions are in brackets. So for the handout I gave you, look at item 3 where it says method. Okay, if it's in brackets, see how it says determine and describe appropriate equipment? Okay, so if it's in brackets, that means it's something you'd only do if you were designing the experiment. Now, the experiment you're doing this week, you didn't design that experiment. I'm giving you a handout with the procedures that are clearly outlined. And so you'll just do the things that are outside the brackets. But later in the semester, when actually you design the experiment procedure and you decide what the data table is going to look like and all those things, then those things, the words that are in brackets will apply to you. So some of the stuff doesn't apply for a lab report, like item number 5, you don't have to create your own data table for collecting the data. You do need to put a data table that summarizes the data in your report, but in the handout I gave you, I already provided a data table that you can write the numbers down into that you're going to be collecting. All right, so we'll talk more about that in lab today. If you have any questions, look it over, and we can talk about it in lab. But just since we're here all together at once, I thought I'd give you the handout and briefly introduce the idea of the rubric. All right, so your next homework assignment is listed there. Homework 3B is due next Tuesday before class. For problem 66, I think it's like asking a yes-no question or something like that. What I wanted to emphasize is you need to explain your answer. You know, don't just say yes and that's the end of the problem, but actually give some details to show that you understood the fluid mechanics there. All right, so what we're going to be doing now is taking the ideas of pressure, applying that over surfaces, and then find out the magnitude of hydrostatic forces. Now, this is some of the really important stuff from the course. You know, some of the main information that you might expect to see on the FE exam. You know, these kinds of problems are really popular because these are like good questions you can ask in 2 or 3 minutes, and it's easy to assess. So hydrostatic forces is important stuff. Just to lay the groundwork for what we're going to do in hydrostatic forces, I'll remind you of the idea of centroid and the concept of the area moment of inertia. I got dark quick. I'm still figuring out what each of these different settings here means. Let's try AV mode. All right, that's better. This is from your book. It shows the formulas that you can calculate the centroid and the area moment of inertia for a variety of different shapes. And you'll see later today why this becomes important, but I just encourage you to either print this off at full size and have it as a reference, or memorize these formulas, or it's in the back of your book, it's available. But we're going to need to know the location, the center of area, and then the area moment of inertia, which is, in a physical sense, you can think about the resistance to rotation about a certain axis. But it has kind of a different meaning when it comes into the fluid mechanics, and so we'll get into that in just a bit. All right, so this is the type of problem we're going to try and solve. And think about, you've got a body of water being held back by a gate. And in this little drawing here, it shows that we've got 4-meter depth of water and a gate that is holding back the water. And maybe the question would be, how hard is the water pushing on this gate? You can see it's exposed to the air. Here's the interface of the air and the water. And so we'd want to find out not just the pressure at a certain depth, but the entire force of that pressure acting over an area. We know from previous lectures and even before that force is pressure times area. How does the pressure change as we go down through a fluid? It increases. And in fact, it increases at a linear rate. The unit weight, gamma, is the rate at which pressure is increasing, because delta P is gamma times delta H. And so gamma you can think of as the slope of the line as the pressure is accumulating. So here is a different view of that same plate. This is showing it has a certain height, and then this dimension A is the distance into the page that we didn't see with the first image. Now, the dimension B here is showing from the water line down to the bottom of where that water is in contact. And so B is not to the top of the physical gate here. See that there's part of this 1 meter that's in contact with the air. In problems like this, it only matters where the water is in contact with the surface. And so below that interface of the water and the gate, that also isn't going to contribute to the force of the water pushing on the gate. But that just gives you kind of an idea of the types of problems we're going to be solving. This is one of the simplest because the gate is vertically oriented. Some of the complications that we'll have in coming examples are going to be when the gate is at an angle. That'll make our calculations a little more complicated. Or if the gate is curved instead of being flat. We'll have to follow kind of like a more complex procedure for breaking a curved gate down into pieces. But this green triangle here is showing the pressure distribution as we go down through the fluid. And so the pressure of the liquid at the top is 0 because it's in contact with the air. But then the pressure is gradually increasing as we go down through the fluid. And it's increasing at a constant rate equal to gamma. And F is the equivalent hydrostatic force that we would be interested in knowing. Not only the magnitude, but also the location of that equivalent force. Now this is something that I really want to emphasize, is that it's not that there's just one force at one location here, but we have a variety of pressures acting over a certain area, and what we could do is we could represent that magnitude as a single force acting at a single location. And so it's the equivalent of this one force at a certain point has the same equivalency as a pressure acting over an area. So it's kind of like we're integrating pressure times area over the entire surface of this shape and then representing its magnitude by F at a certain location. The centroid of this shape is going to be important in solving problems like this, and we can get the centroid from that slide I showed you just a few moments ago. If it's rectangular, then the location of the centroid is going to be at 1/2 of A. So in other words, in the middle, speaking horizontally, and then vertically it's going to be 1/2 of B. But the center of area that we're interested in isn't the center of area of the gate itself. It's the center of area where the gate is in contact with water. So we would be careful to identify the centroid to be half of B and ignore the piece of the gate that's below the water surface and the piece of the gate that's up here where it's in contact with the air. All right. Now, things are a little bit different if the gate actually doesn't go all the way up to the water surface. You know, in this figure, we had this triangular distribution of pressure. The pressure started at 0, and it was gradually increasing as we went down. So it started at 0 at the edge of the gate, which is where we were interested. But now the gate is all the way submerged. And so the pressure distribution, we have our centroid still, our pressure distribution doesn't start at 0 at the top edge. We have it 0 at the water surface, but the pressure is increasing, and then we have some positive pressure there. And so the reason I bring it up is that in problems that look like this, where the gate goes all the way to the top surface, it will be easier to identify the location of F. Because of that triangular distribution, there's a little shortcut we're going to be able to use that we can't apply in cases like this. In cases like this, we'll have to use a more thorough approach that we have a formula for, but it's not just going to be an easy shortcut of knowing that in a triangle the center of area is 2/3 of the way down, like we could in the first case. So we'll still find some force, but in a case like this, the force is closer to the centroid. I kind of spilled the beans on the shortcut with this one. The center of area for a triangle is 2/3 of the way down, right? Or 1/3 of the way from the bottom is the center of area for a triangle. And so the location of this hydrostatic force is just going to be whatever the distance is, 4 meters. All right, so 2/3 of the way down, 4 meters, is going to tell us the location of the hydrostatic force if we have a triangular distribution and it's all the way up to the air surface that the pressure begins accumulating. And so it's a certain distance away from the centroid. But when we have the gate submerged in water like this, then the equivalent force is closer to the centroid than it was in the previous example where we had a triangular distribution. And so we're going to have a formula for calculating how far away from the centroid is the force applied. All right, so let's define some terminology here, and then we'll begin working on our first example. First of all, we have delta H, which measures the distance from the water surface to the centroid. And so here, think of it this way. We've got some inclined plate, and it has a length of A and a width of B. Now B, we have to dimension in a side view of it because in a different side view because we can't see how deep into the page it's going when we're looking at it from this edge case here. But delta H is the distance straight down from the water surface to the centroid of that object. And so it's a vertical distance from the water surface to the centroid. And the reason why we care about delta H is we use delta H to calculate the pressure at a certain location. And for our purposes, it's going to be important to know the pressure at the centroid, of that plate. So we calculate the pressure at the centroid with simply the hydrostatic equation. Now, y bar is the inclined distance from the water surface to the centroid. And so what I mean by inclined is where delta H was a vertical distance straight from the top of the tank down, y bar is inclined in the same direction that this plate is pointing. So let me draw on the board here, since I used to be able to draw right on the screen, but they don't like it when I do that nowadays. Okay, we've got a tank of water. We've got our water surface. Here's the plate. All right, so delta H is here. vertical, and now here is our y bar. Y bar is the inclined distance from the centroid to the water surface. Okay. Now YCP is also an inclined distance, but it's not measuring from the centroid, it's measuring from where the equivalent hydrostatic force is applied. So we've got some hydrostatic force that's acting on this plate, and here is our YCP. YCP is the inclined distance from the centroid to the location of the force application. So CP stands for center of pressure, and that just means where the equivalent hydrostatic force is. And so in these previous drawings, the force is applied here. This is the center of pressure. The centroid is the center of area, but the center of pressure is where the force is applied. And in this drawing, before it, we had the center of area, which was the centroid, but the force was applied at the center of pressure. So here's our CP. Yes?
Is the distributive load always in a linear fashion?
Yes, it is. All right, so here's the formula to calculate YCP. We can find the inclined distance from the water surface to where the force is applied by knowing y bar, which is the distance from the surface to the centroid, and then I, which is the area moment of inertia for the shape that the force is acting on, divided by y bar A. We're going to use this formula several times today, so you'll get some practice applying this formula, and then interpreting the geometry is sometimes the hard part. Sometimes, you know, the challenge isn't plugging the numbers into the formula. Sometimes it's just the trigonometry of remembering a 3, 4, 5 triangle, or, you know, if you've got a 30-degree angle here, what's the distance there, and so on. It may be that we're a little bit rusty on our trigonometry, but we'll get some good practice over the coming few lectures reminding ourselves of all those things. So let's go back to this example. I said this is the type of problem we're going to be solving this semester. Let's put some specifics in here. Let's say that this is water at 20 degrees Celsius. Okay, since it's 20 degrees Celsius water, then that tells us to use a different unit weight than we sometimes do. If we go to the back of the book and look up the gamma for water at 20 degrees Celsius, it turns out that the unit weight is 9790 newtons per meter cubed. All right. And the example asks, what's the magnitude and the location of the hydrostatic force? And then, what's the magnitude of F? Because F is the force that's pushing to keep the gate closed, and what we've got is hydrostatic forces that are trying to open the gate. So if this is our gate, here's the water, then there's a hydrostatic force that's acting in this direction, and then F is trying to keep the gate closed. And so it's going to be in an equilibrium there. F, the moment distance is 4 meters, whereas we don't yet exactly know the location of the hydrostatic force that's being applied. All right. So, magnitude and location of the hydrostatic force. Here's the procedure that I'd like you to consider. First of all, find the distance to the centroid. So, find delta H. Okay? So, this is a rectangular shape. We've got A is 3 meters, B is 4 meters. So from that, just by inspection, we know the center of area is going to be 1/2 of 4, since it's rectangular. So delta H is 2 meters. Okay? Now we use delta H in order to find the pressure at the centroid. So find P bar. And P bar is the variable that means the pressure at the centroid. And so P bar is simply delta H times gamma. Okay, so we want to know how much pressure is there at the centroid. 2 meters down into the fluid. So that's just 2 meters of 9790 newtons per meter cubed. All right, so the pressure at the centroid is 19,580 newtons per meter squared. Now, the next thing is we want to find the hydrostatic force. So find F sub H, hydrostatic force. And that's simply the pressure at the centroid multiplied by the area. Okay, so we know the pressure at the centroid is 19,580 newtons per meter cubed. Now what should I use for area? 3 by 5. Why is it not 3 by 5? Because we only care about where the water is in contact with the gate, not where the air. The air isn't contributing to the hydrostatic force. So the area that we're going to use is 4 meters by 3 meters. Okay, so the area is 12 meters squared. And so the hydrostatic force magnitude is 234,960 newtons. So that's how hard F sub H is. Now, its location, 4. Find the location of the hydrostatic force. Anybody remember the shortcut method I told you? 1/3 from the bottom or 2/3 down from the top. And so that would be, so this shortcut, the force, the hydrostatic force is 2/3 of 4 meters downward. And so that says it's going to be 2.667 meters from the surface. Okay, well, let's try it the official way rather than the shortcut way. And we'll see if the official way gives us the same idea. Now in this, we first of all have to find out what is y bar. Do you remember what the definition of y bar was from the previous slide? All right, the slant distance from the centroid to the water surface. Now, to differentiate, delta H was the vertical distance from the centroid to the surface. But this plate is vertically oriented, and so the slant distance and the vertical distance are the same. So if you have a vertically oriented surface like this, y bar is equal to delta H. So that makes it easy. That's kind of why the vertically oriented plate makes problems easier for us, is delta H and y bar are the same. So it's equal to 2 meters. Okay, now we have to also, in this step, calculate the area moment of inertia. For a rectangle, it's AB cubed divided by 12. Now luckily it says which is A and which is B already for us. But if you can't quite remember, like which one is the dimension that you cube, it's the vertical one. You know, in hydrostatics, vertical depths and vertical dimensions are more important because that's the direction in which pressure accumulates. So here what we're saying is we have a width of 3 meters multiplied by 4 meters cubed divided by 12. All right, so the area moment of inertia should be 16 meters to the 4th. And we use that delta, the y bar and the I to calculate YCP. So YCP, our formula from the slide before, was y bar plus I divided by y bar A. Okay, so it's 2 meters plus 16 meters to the 4th divided by 2 meters, and then the area is 12 meters squared. So I see some of you following along with your calculators. If you do, I think you'll find that this second piece of it here is 0.667 meters. And so the YCP is 2.667 meters, which we kind of already knew, because this is one of those cases where we have a triangular pressure distribution acting on the face of that plate. So what we're saying is, from the water surface down to where the force is applied is 2.667 meters. That's how deep we go for the equivalent force. Now in reality, it's not like there's one magical single force that's applied at one location in the plate. It's just that there's a little bit of force at the top, a little bit of force a little lower, and so the average location, if we represent that entire distributed pressure acting over an area, then that resultant hydrostatic force is at a depth of 2.667 meters. Because the center of area of a triangle is where the center of pressure is located. Are there other questions so far on the steps that we've done? This is new stuff. This is the first time you've seen hydrostatic forces, and so you won't get into a rhythm until we've done a few of these, but after a while you'll be able to knock these out like they're nothing. So what's our last step here? If we want to find F, if we want to find this force, the force required to keep the gate closed, because the hydrostatic forces are trying to open the gate, what's the last thing we need to do? That's right. Yeah, so our step 5 is summation of moments. And so we have, let me move step 5 over here to the other side since I don't want to crouch down too low. All right, so step 5 is we have 234,960 newtons, which are acting counterclockwise at a distance of 2.667 meters from that pivot point. That's pushing it counterclockwise, and then pushing clockwise is the force F, and it's acting at a moment distance of 4 meters. Okay, so from that we can get that F needs to be 156,640 newtons in order to keep the gate closed. All right, so I've done chicken scratch up on the whiteboard. Let me bring up a slightly neater version of that same example in case someone is following along in the video. We started by, just to summarize, the distance to the centroid. So delta H is a vertical distance to the centroid. So it's 2 meters. And then we want to find the pressure at the centroid, so we use the hydrostatic equation for that. And then if we know the pressure at the centroid, we can find the equivalent hydrostatic force by multiplying that by the area. So that's where we got 234,960. And then our final step was to the locations of these forces. And so the location of hydrostatic force uses the area moment of inertia formula, uses the YCP, and then we find where the force is located, and then the resultant force to keep it closed is going to be a moment equilibrium problem. So questions? I don't think there are any. I think, assuming that, there's maybe concrete on either side of this gate, this gate is all we're focused on.
How come the force is going to the left versus
Oh, well, there's a force up here at the hinge.
right? Oh, okay.
Yeah, right. Yeah, thanks. I didn't see what you were asking. Yeah. Okay, so that's your first taste of hydrostatic forces. What I'd like you to do now is consider this. This is, again, just a vertically oriented plate, but things are a little trickier here. We can't use that triangular shortcut like we did before. You're going to have to apply the full-fledged procedure to find the location of the force. So we've got a gate that's 3 meters tall and 2 meters wide. It's holding back water at 20 Celsius, and so again you're going to use 9790 as the unit weight. Now the dimensions are that h is 6 meters, and so what you need to do is find the magnitude and the location of the hydrostatic force. So this isn't where we're asking how much to keep it closed. This isn't like that last moment analysis step. You won't need to do that. But I do want you to find, first of all, same procedure, find out what is delta H, what's the pressure at the centroid, what's the magnitude of the hydrostatic force, and then where is it located. All right, so the same basic outline of equations and steps, but a few different dimensions. So I'm going to pause the recording, give you some time to work on this, collaborate with your classmates, and then see if you can find these two things, magnitude of the force and the location of the force. Okay, I drew over here on the whiteboard a little bit more detail as far as the drawing goes, because we know that the distance from the water down to the bottom is 6 meters, but we need to know the distance not just from the edge of the gate to the centroid, but from the water surface to the centroid. And so delta H goes from the water down to the middle of the gate. So actually, as it says here on the screen, delta H should be 6.5 meters. So sometimes it's not necessarily even the fluid mechanics that makes it challenging. It's just kind of getting the dimensioning right or the angles of things. Okay, once you know delta H, then you find the pressure at the centroid by multiplying the unit weight by that distance. And then the force is the pressure times the area. Okay, so who got 264, 330 newtons? Good, good. Now the location of it is where we start to use this formula for YCP. And again, it's a vertically oriented gate, and so we're fortunate that the Y bar equals delta H. Nice and easy. So we can just substitute in 4.5 meters for the Y bar distance. And for the area moment of inertia, we should use A is 2 meters and B is 3 meters. Let's go back to the original problem here. Okay, so it's 2 meters wide, 3 meters tall, and the area moment of inertia is AB cubed divided by 12, where B is the vertical dimension. Yes?
So what's the Y bar is not of the object?
What?
The Y bar you had as 4.5, so it's not the Y of the object, like of the gate.
That's right. Yeah, it's not the it's not a distance that has to do with the gate. It's the vertical distance. No. Y bar, the definition of Y bar is the inclined distance from the centroid to the water surface. And so here, the gate is only 1.5 meters up to the edge, but then to the water surface is an additional 3 meters beyond that. Are there other questions related to this example? All right. Now, Like I've been talking about how lucky we were that these were vertically oriented gates, right? Well, they couldn't stay vertically oriented forever. We got to look at what happens if it's at an angle. How is it going to be a little bit more complicated to get the geometry right and so on. Okay, so this gate is still rectangular. It's 2 meters wide, 3 meters tall, but now it's oriented at a 45-degree angle. And what's going to make this a little bit challenging is that y bar does not equal delta h anymore. So we're still going to follow the same procedure though. We're still going to, number 1, find the depth of the centroid. Number 2, find the magnitude of the hydrostatic force. Number 3, the area moment of inertia. So let me write these steps here so you can get started on this. Number 1, depth to centroid. And that is delta h. And then number 2, magnitude of force. So the force magnitude, the formula for that is P bar times area. Well, that's kind of building in the hydrostatic equation into this step. What I mean is we're going to have delta H times gamma to get the P bar, and then multiplied by the area there. All right. 3 is going to be the area moment of inertia. So we're going to calculate the I for the gate, and then 4, finally, the location of the force. So let's take a moment together to break down the geometry here and see if we can figure out how to dimension this gate that's at an angle to make sure that we get the correct y bar, the correct delta h, the correct ycp, and so on. Okay, so we have the water surface. Here's our gate. From this front view, we can see that it is 2 meters wide. Okay, from the side view, we can see that it's 3 meters tall. Why couldn't I dimension this as 3 meters? Why couldn't I say from that edge to that edge is 3 meters? Because it's at an angle. If we were looking at it straight ahead, then the height that it projects isn't the same thing as its actual physical length. So it's the physical length of the gate, not the vertical component of its length, but it's the physical length of the gate plate. This one, I guess, isn't a gate, but it's the actual length of 3 meters that we need to know for the area moment of inertia formula. Okay? All right. So in this side view now, here's our plate, and it goes up at an angle. It's a 45-degree angle. All right, so here's the centroid of it. Remember, delta H is defined as the vertical distance from the centroid to the water surface. Y bar is the inclined distance from the centroid to the water surface. And then here's going to be some equivalent hydrostatic force. So ycp is the distance from where the force is applied up to the water surface. All right. So you're going to need to do a little bit of trigonometry on this one to find out if we know it's 5 meters down to this top edge. So in other words, this is 5 meters down to there. How do you get delta H when you know it's 5 meters to the edge, it's at a certain angle, this overall gate is 3 meters, and so on? I'll give you a moment to struggle with that, check what you think is the right answer with your classmate, or I'll be circulating around with actually what is delta H, so that then you can go through all the rest of these steps in turn. We know that this gate is 3 meters long, right? So the centroid is going to be in the middle of that. How do we find the vertical component of that 1.5 meters? Because it's 1.5 from the edge to the centroid, but it's only the vertical component of that 1.5 meters that counts as delta H. Any ideas? Yeah. Just divide by the square root of 2. Why is
Vertical force gets a 45.
okay? It's a 45-degree angle, right? So you can use the sine of 45, you know, 0.707. That's going to tell you the vertical component of the 1.5 meters, which is the overall length. We want to know the vertical contribution, you know, because that's what adds into the delta H. I'll give you a few more minutes to work through this, and then I'll bring the solution up on the screen. 9810. All right, so first things first on this one, we want to find the depth of the centroid. So it's 5 meters to the top edge of the plate, so it's going to be at least 5. But then we know that it's 1.5 inclined meters from the edge to the centroid, but we only care about the vertical component of that 1.5 meters. And that's why here I've multiplied the sine of 45 by 1.5 to get that the delta H is 6.061 meters. So that delta H is what's going to govern the magnitude of the force, because that's the distance that's going to govern the pressure at the centroid. And the pressure at the centroid is what gives you the force. It's force times the area multiplied by the pressure at the centroid. So, any questions about the geometry of this first step in finding delta H? I was never any good at trigonometry, and now I'm just slightly less bad than I was in middle school. Yeah, that's when I learned. It was in, what, 7th grade or something? But I've struggled through hydrostatics enough times that it's starting to make a little sense to me now. Magnitude of the force. Everybody get 356.7 kilonewtons? Or if not, then this makes sense at least. So I want to emphasize that it's a little tricky knowing sometimes whether it's the vertical component of something or its actual physical dimension. And so here, we use the actual physical area of the plate. It's not like we're only finding the vertical area of the plate. It's the actual physical area of the plate that we put into that hydrostatic force equation. All right, so now area moment of inertia, actual physical dimensions again here. And then the location of the force, I've done a little sketch here just to show how you calculate the y bar. So we had the delta H was 6.061, so that's the vertical component of that triangle, and we want to find the hypotenuse of it. So it's going to be the vertical component divided by the sine of the 45 to find the y bar. And then we put that into the formula for YCP. Okay, so depending on how much precision you carried through in your calculator and your round off and so on, it should be about 8.66 meters is the YCP. And so that's the inclined distance from the water surface to where the hydrostatic force is located. So now, where these problems get tricky then is like, well, I'll bring it back, don't worry. We've got the YCP, so that's the distance along this line down to where the force is located. But what if then we had another force and you're having like a hinge at the edge of the plate? So sometimes, even though you've calculated YCP, then you have to take that distance and then put it in terms of where along the actual plate is the force located. Because right now the distance is relative to the water surface. And so there can be an added level of complexity there once you've calculated the YCP sometimes having to take the distance back into another frame of reference. Okay, so does this need to stay up any longer, or I'll leave it up just a minute longer. And of course, the video will have all of this. You can do like a frame-by-frame stop. If I ever scroll through something too fast, you can freeze frame it real quick, hopefully, and copy down what you need from that. All right, so we've done rectangular gates so far. Our next example is going to look at a circular pipe and how it intrudes into a body of water if we cut the pipe at an angle. All right, so here's the scenario. We've got a pipe coming in, and if you cut a pipe at an angle, then the opening of that pipe is actually going to be an ellipse. And to prove that to yourself, roll up a piece of paper. All right, so the end of it is a circle right now, but see, circle. If you cut it at an angle, though, it's not going to be a circle anymore. It's going to be elliptically shaped. And so here I've given you the formula to calculate the area of an ellipse and the area moment of inertia of an ellipse. So we want to find out on this how much force is required to open the gate. So you see the F that's indicated there, that's an opening force, and there's also a hydrostatic force which isn't shown, but the water is pushing that gate closed. There's a gate covering the opening of this pipe. We want to find out how hard would we have to pull in the direction indicated in order to begin to open up the gate if the hydrostatic forces are trying to keep that gate closed. So the procedure here, as always, is you're going to want to first of all find out where is the centroid, what's the depth to the centroid, delta H, then what is the inclined distance to the depth of the centroid, y bar, what is the YCP, and then this is going to be one of the situations where you'll calculate the YCP, but that's telling you the inclined distance all the way up to the water surface, but we want to know distances relative to the actual hinge itself. Now, let me mention one other thing. The definition of y bar, for example, is from the centroid following the angle up to the water surface. Well, we've got a problem, because if you follow that centroid in the same direction, then there is no water surface after you get past that wall. So what you do is you would extend the water surface at the same elevation that it was before. So the y bar is following this up to here where the water level would be. It doesn't matter that this wall is here, or it could be a foot to the left, it could be a foot to the right. That's not going to change the pressure at the centroid. It's not going to change the location of the hydrostatic force. And so what I'm saying is extend the water line towards the right, and then y bar is from the centroid up to where it would intersect with the water line if you extended it in an imaginary line to the right. All right. So one more hint before I turn you loose on this. We've got a triangle that is, let's see. We know that the diameter of the pipe is 4 meters. Okay, so that is this dimension, and the physical height of the elliptical gate is 5 meters. So what's the magic number here? Okay, right, 3 meters. So that will be useful in figuring out some of the geometry in terms of how this extends up to the surface and what the distance is from the centroid, because we've got 8 meters from the top edge of the gate to the water surface. So, all right. Okay, I've got the solution up on the screen here if you want to double check some of your work so far. The first thing to take a look at is that whereas A and B were entire widths and heights when it came to a rectangular gate, here the definition for the ellipse, A is just half of the width of the ellipse and B is half of the height of the ellipse. So that means A is 2 meters, B is 2.5. So when you calculate the area, you need to use the right dimensions there to get 15.708 meters squared. So the magnitude of the force is going to be, first of all, using the depth of the centroid. So it's 8 meters to the edge, and then this vertical dimension of 4 meters, it tells you it's 2 vertical meters from the edge down to the center of the gate. So the overall total delta H should be 10 meters. And then to calculate the magnitude of the force, you'll just multiply the depth by the gamma by the area to get 1.541 meganewtons. And then what I did to calculate the y bar is just use the idea of similar triangles. That is, if we have a 3, 4, 5 triangle, and then the y, which is the y is the inclined distance to the centroid, where 10 was the vertical distance to the centroid, then we can calculate y as 12.5. Okay, so that means it's in the direction from the center of the gate back up to the water surface, 12.5 meters. All right. So then we need to calculate the area moment of inertia, 24.544 square meters. Now, here's the formula for YCP, and it's more useful than actually calculating the actual YCP, which is all the way from the where the force is located up to the water surface. It's more useful to calculate the distance between the centroid and the YCP, because the centroid is relative to the actual location on the gate itself. So over here on the whiteboard, what I've said is this gap distance from where the force is located to the centroid is YCP minus Y bar. And so we can calculate this quantity YCP minus Y bar, and then because we're doing a moment balance at the end, it'll actually be somehow more beneficial, because we'll just calculate this gap distance plus the distance from the edge to the centroid, which is 2.5 for this. So it'll be that gap distance plus 2.5 would then be the moment distance we need. So back here to the solution. I find that gap distance is 0.125, and so then the moment distance is you've got 5 meters of distance and the F, which is trying to open the gate, and then you've got 2.625 meters, which is the 2.5 meters to the centroid plus the gap distance additional of 0.125 and the 1.541 meganewtons. So I'm going to leave this up on the screen for a few minutes. We're out of time for today, so I'll turn you loose. I'm going to pause the recording, and we'll pick back up with hydrostatic forces on flat surfaces when we get together in class on Thursday. But remember, we got lab today and tomorrow afternoon, so I'll see you then.